Hey everybody, it's Monday, April 19th, and in today's video, I want to go over a very nice problem that I assigned to you last Friday. There's really only one reason why I want to give you this problem. And the reason why I want to give you this problem is because a couple years ago, I inadvertently completely screwed up a bunch of my students because, frankly, they didn't get enough of an opportunity that particular year to mess around with this idea. So on the AP test, many years ago, there was a question about one block being dropped on top of another block and sticking at the position shown in figure 2. And on the simple harmonic motion test at the very end of the year, shortly before the AP test, I had my students take a simple harmonic motion test with a multiple choice question about the block being dropped on top of the other block at the amplitude. And a lot of them got it wrong, and I said, hey guys, I think this is going to be really important. They haven't asked a simple harmonic motion question in a while. You should be prepared for it. And what do you know? My prediction was exactly correct. They did ask a simple harmonic motion question. And it did have to do with the mass being dropped on top of the block. Oh my God, how could we be so lucky? The only problem is they asked this version of it, which, as it turned out, it's not exactly the same. So in order to avoid this kind of scenario for this year, especially because this kind of problem, I think, is a pretty good candidate because it is conservation of energy. You got your simple harmonic motion. There's a lot of different topics involved in this question. I think this question is important for us to think about. And so this one is not exactly from the College Board. I made this one up. But hopefully you got a chance to play with this simulator. And so you have gotten a little more of a feel for how this works. And so what I want to do now is go through both scenarios, talk about the differences, talk about why the differences are, in fact, differences, to sort of allow you to check whatever work you might have done for this problem. Okay, so I'm going to start the simulator off at the end. And so first, I'm just going to let it run. We'll watch what happens. We'll watch what happens to these values over here, the amplitude, the maximum velocity, the period, the total mechanical energy. We'll see how they compare, and then we'll try to work through why. All right, here we go. All right. So I think just looking at it, we can observe a couple of important things. It's definitely now taking longer to go back and forth. And so the period increased. That makes a lot of sense. The period is directly proportional to the square root of the mass. We had 1 kilogram, or in this simulator, 1 kilogram of mass. Now we have 3 kilograms of mass. Now on the worksheet, I just labeled the masses as m and 2m, but either way, the mass increases by a factor of 3. And so, of course, the period is going to increase since the period is directly proportional to the square root of the mass. Okay. Now, that also, I think, just makes a lot of conceptual sense, even if you don't think about it in the context of the equation, because now the system has more inertia. And so, of course, it would take a longer amount of time to go back and forth because the spring force at any given point has not changed. The spring constant hasn't changed. And so it's harder to move 3 kilograms or 3m than it is 1 kilogram or 1m. And so it makes sense that it would take longer for it to go back and forth. Now, on the sheet of paper that I gave you, I'm sorry, not there. On the sheet of paper that I gave you, the first thing that I asked you to address was the total energy. And I think the weirdest result here is that the total energy is the same. Now we should work through why that is. Now, when I tell you in this problem, the block is dropped onto it and immediately sticks to the block of mass m, there needs to be an alarm bell going off in your head. Ding, 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 ding. 2 blocks just collided and stuck to each other. It's a perfectly inelastic collision. And so the basic idea here is that in a perfectly inelastic collision, the kinetic energy is not conserved. But it was dropped at the end, at the amplitude. And the reason why the total energy remains the same here is because there was no kinetic energy when the block was dropped. And so if you are thinking, well, in a perfectly inelastic collision, isn't the kinetic energy supposed to decrease when they collide? Yeah, that's the general rule. But if the original kinetic energy was zero, how could it possibly decrease? And the idea is it doesn't. And so because the collision occurs at the amplitude here, there is no loss in energy due to the inelastic nature, or I should say the perfectly inelastic nature of the collision, because it had no kinetic energy to lose there. That's the idea. Now, we said the other day that when you're doing an experiment like this, you decide the amplitude in these kind of problems, because the object is always going to start at the equilibrium position. And when you pull the spring back, when you displace the object from its equilibrium position, you are determining its maximum displacement from the equilibrium position. And so the total energy in the system first manifests itself as elastic potential energy. Now, obviously, this thing was originally moving, and then this 2 kilogram mass was dropped. But the idea is these situations are essentially the same. The thing is at rest. It's at this amplitude. Now it has this much mass, but that doesn't really matter because the energy first manifests itself as all elastic potential energy, because no matter how much mass it is, it's not moving. So it doesn't have any kinetic energy. All of the energy is elastic potential energy. And since the spring constant is the same as it originally was, and the amplitude is the same as it originally was, the total energy, or the work put in here, as we called it the other day, can be calculated by finding 1/2 Ka squared. And so, because the amplitude is the same, and the spring constant is the same, the elastic potential energy is the same. Now notice I went and I answered C first, but understanding the answer to B is really best determined by understanding the answer to C. Because if we recognize that because the total energy is the same here, and that means the maximum elastic potential energy is going to be the same, then it automatically tells us the maximum kinetic energy has to be the same too. Because this problem just involves a conversion of elastic potential energy here at the amplitude to the maximum kinetic energy here at the equilibrium position. Now, some of you might be looking at the data from the simulator and thinking, wait a second. It says the original maximum velocity was 10 centimeters per second. We don't really care about the unit. Let's just call it 10. And the final maximum velocity was 5.7735. It slowed down. How is it really possible that the total kinetic energy is the same if the maximum velocity decreased so much? Do not forget, and I'm actually going to reset this, that the original maximum velocity was 10 when only the 1 kilogram block was moving. Now you have an effective increase in mass. It actually increased by a factor of 3. So of course the velocity would have to decrease even for the kinetic energy to be the same in general, because now you have more mass. And of course, I hope everybody realizes that if we calculate the kinetic energy of a 1 kilogram block moving at that speed, 10 centimeters per second, and now we calculate the kinetic energy of 3 kilograms of mass moving at that velocity, 5.7735, we would in fact see that the kinetic energy stays the same. And it's because when the block is dropped, it has the same amount of elastic potential energy as it originally had. And so it has to have the same amount of kinetic energy at the equilibrium position. That's the idea. All right, now the next two questions were about the maximum speed and the amplitude, which we've kind of already addressed, but let's just go ahead and get it one more time. Because this 2 kilogram block was dropped onto the 1 kilogram block at the amplitude, this thing had an energy proportional to the amplitude here. So if it had an elastic potential energy, which was proportional to the square of that 10 centimeter amplitude, then when it oscillates back and forth, and all of the kinetic energy at the equilibrium position is converted to elastic potential energy again, then it has to have an elastic potential energy proportional to the square of that amplitude. So because the original elastic potential energy is now equal to the elastic potential energy of this new system, which has more mass, then it's going to have the same amplitude because that elastic potential energy is proportional to the square of the amplitude. Now, following that through, well, if it had the same amplitude, then it had the same elastic potential energy. And if it had the same elastic potential energy, then at the equilibrium position, it has the same kinetic energy. Then the argument about the maximum velocity is quite simple. If 1 kilogram of mass had a certain amount of kinetic energy, which is now the exact same amount of kinetic energy possessed by 3 kilograms of mass, then just by proportional reasoning, the only way 1/2 mv squared can work out to be the same number when the mass is now a bigger number is if the velocity decreases. And again, conceptually, it makes a hell of a lot of sense that the maximum velocity decreases because you now have more mass being moved by the spring. And so the fact that the new system with a mass of 3 kilograms has more inertia than the old system, which had a mass of 1 kilogram, then of course we would expect this new system to move slower, which, looking at this thing, it very clearly does. Okay, so now that we've covered every aspect of the situation where the block is dropped on top of the other block at the amplitude, now we're going to talk about what happens when the block is dropped on the oscillating mass at the center, or in other words, at the equilibrium position. So we'll let it go and we'll observe what happens. Here it goes. Okay, so the first thing to notice is that the most important difference, or at least in my opinion, what the most important difference about this is that this block is going to be dropped on top of the oscillating block at the equilibrium position. And so the big question here is, well, how's that different? And I think the easiest way to think about how it's different is to first think about how it's the same. It's the same because it's an inelastic collision, or I should say a perfectly inelastic collision, because the objects collide and they stick together. Why it's different is because now the objects are engaged in a perfectly inelastic collision when the 1 kilogram block is moving. And so when I hit start, the block is going to drop. And now because this block has kinetic energy when it collides with the other block, that means there is kinetic energy available to be lost in the collision. That's the idea. And so because the 1 kilogram block has kinetic energy when the 2 kilogram block is dropped on top of it, some of that kinetic energy that it has is lost. That's fundamentally different from what happened in the other scenario, because when that block was dropped, it was dropped when the 1 kilogram block had no kinetic energy. So there was no kinetic energy available to be lost. However, in this scenario, when the 2 kilogram block drops on top of the 1 kilogram block, it's dropped on top of it when it's moving. And so because it has kinetic energy, it's able to lose some of that kinetic energy. And so this situation is fundamentally different than the last one. So now we just have to ask ourselves the question, what's different? What's changed? And in order to do that, I think we should just methodically go through all of the questions that were answered. So the first question that was asked was about the total energy. And so I hope it's pretty clear to everybody that if this is a perfectly inelastic collision, when the 1 kilogram block is moving, the total energy present in the system has decreased. And it's decreased because some of the energy that the system had
was lost as heat in the perfectly inelastic collision. The total energy went down. And so because some of that kinetic energy was lost in the collision, part B is a super easy question to answer. When the block crashed in to the oscillating block, it had its maximum kinetic energy, which subsequently decreased due to the nature of the perfectly inelastic collision. So the maximum kinetic energy is less. And now let's be clear here. We can tell that it's less by looking at the numbers in the simulator. Because I don't know if you realize this, I guess I can just show it again. The maximum speed, maximum velocity decreases in both scenarios. But notice in the scenario where it's dropped at the end, the maximum velocity ends up being let's call it 5.8. In the scenario where it's dropped in the center, the maximum velocity decreases. It should. There's more mass now, so it definitely should decrease. But notice it decreases far below 5.8. Now it's only 3 1/3. The maximum velocity decreases not just because the mass increased, but because the kinetic energy that the 1 kilogram block originally had is no longer present in the system. Some of it was lost because this is a perfectly inelastic collision. Now I'm going to reset this and start this one more time because, let me just pause it. The next question is asking about the maximum elastic potential energy. And I think the most important thing to keep in mind about this problem is it's a conservation of energy problem. Whatever amount of kinetic energy this thing has at the equilibrium position is converted to elastic potential energy at the amplitude. So the fact that as soon as these blocks come into contact, now there's less kinetic energy present in the system, well, of course there's going to be less elastic potential energy present in the system now, because the only reason there is elastic potential energy at all is because of the conversion from kinetic energy to elastic potential energy. And if there was less kinetic energy to be converted to elastic potential energy, then obviously there's going to be less elastic potential energy. We can clearly see that from looking at these numbers. The mechanical energy goes down because of the nature of the perfectly inelastic collision. And once again, we've already addressed it, but the last two questions there ask about the maximum speed and the amplitude. Now, it's not quite enough to say that the maximum speed decreases because there's more mass. The maximum speed decreases here even more than it did in the previous situation, because not only is there more mass, but now there's also less kinetic energy than there was initially because of the nature of the perfectly inelastic collision. So the fact that this thing is dropped when it has kinetic energy means there's kinetic energy lost, and so because there's now there's less kinetic energy, there's less maximum kinetic energy, and so there's less of a maximum velocity. You couple that with the fact that there's now 3 times the mass, well, it's even that much less of a maximum velocity. And as we said, because there's energy lost, when that maximum kinetic energy is converted to that maximum elastic potential energy, there's now less maximum elastic potential energy than there was in the beginning. Because in the beginning, it had the original total energy, but now since some of that was lost in the perfectly inelastic collision, that total energy has decreased, which means when that total energy is taking the form of elastic potential energy, the maximum elastic potential energy is less. So because the elastic potential energy is equal to 1/2 kx squared, when x is equal to a, or in other words, when the position of the object is at the amplitude, the potential energy is proportional to the square of the amplitude. And so the basic idea here is because there is less elastic potential energy, the amplitude is smaller, which we can clearly see from these measurements. Whereas in this situation, when it was dropped onto the oscillating mass at the end, the amplitude didn't change because there was no energy lost. And so we can clearly see by comparing the two situations that the only reason why the amplitude is less is because of the energy lost in the inelastic collision.
All right, everybody. That is it for today. I hope the differences between these two situations makes some pretty good sense to you now, if it didn't already when you first did this problem looking at the simulator. That said, of course, if you have any questions about this, please feel free to reach out via email or comment and let me know. But with that, that's it for today. All right, everybody. Have a good one.